Next one up on the list is going to be energy. Now this one's going to be kind of a complicated topic. This comes in right after forces with the absolute most important stuff to understand on physics. If you've got a firm grasp of forces and of energy, then you can solve a significant portion of any physics problems whatsoever. So these are kind of key ones to look back on and be comfortable with. I'm going to go through with a couple of the equations pretty quickly. Kinetic energy. We always used Ke, sometimes you'll see simply a capital K. Some places even use a capital T just to make our lives more interesting. I don't know why they use a T, but I have seen that before. Kinetic energy is 1/2 mv squared. If there is one equation for energy to remember, this is a really good one. I'd assume most people who have been doing stuff with physics have got this one down pretty well. Another good one, potential energy due to gravity near the surface of the Earth is mgh, where h is your height above some reference point that you can arbitrarily choose. Normally, I like to put it at the lowest point that's going to show up in any of my problems, and I set h equals 0 there. Another common one is potential energy of a spring, which equals 1/2 k delta x squared, where delta x is the compression or expansion of your spring. It's how far it's stretched or squished from your natural length. Very important equation, work. Work equals our force times our displacement times cosine of the angle between the two. Now remember, and I need to draw this in, my displacement is in a given direction and my force is in a given direction. But the result that we get, work and energy in general, are all scalars. They do not have direction. That's one of the things that makes them so useful. And one of the reasons that work can be very useful is because we use something called work-energy theorem, where work is how you add energy into a system or take energy out. This allows you to deal with circumstances where energy isn't necessarily conserved in the usual way. You can have something like friction. You can find the force of friction, you can multiply it along the displacement that it's applied over, and if you need a cosine in there, then you'll probably do that. You'll find that it will end up being a negative, because whichever way you're going, the force of friction always points the opposite way, so you'll have 180, giving you negative work, because friction always takes away energy, it doesn't give you energy, at least in this mechanics approach that we're using. Some of the important things to keep track of is the idea of dissipative forces. Dissipative forces. In other words, air resistance, drag, and friction. These are things that take energy out and don't give it back. We can keep track of those with work. Now, the ones that do predictable work, things like gravity and springs, we've turned them into potential energies, other ways of keeping track of the work that they do. Now, I'm going to remind you that in general, we deal with a lot of the energy stuff by the phrase, by conservation of energy. And I'll remind you my way of remembering that. Conservation means what you start with, you end with. So you start off and you find your initial energy, and you'll end up setting that equal to your final energy. And that'll be your initial kinetic energy plus your initial potential energy. And then that'll be equal to your final kinetic energy plus your final potential energy. And energy can move around, it can go all these different places, but you can't lose any of it. It's got to be accounted for somewhere. It's just good accounting. Find out where it went. It either goes into kinetic energy or potential energy, or if you do lose some, it goes into work of some kind, and you can keep track of it that way, which isn't normally considered conservation of energy, but it's not bad. And so these are the main concepts here. Energy is really, really useful because it is a scalar. That means we don't have to keep track of direction. But there is one huge limitation to energy. There's no... Sorry about that. There's no time dependence. In any of the energies we deal with, you cannot tell how long something will take. That is a huge limitation.